So welcome everyone for another episode of TCS Plus with Chris Peikert today. Um, Before we begin, let me quickly thank my co-organizers, Amin Diante, Clément Canon, Gautam Kamat, Thomas Vidic, and Ilya Rosenstein. Also, maybe we should quickly go around the table as we usually do. So here we have the group from University of Ottawa, Anne Bodment and others. Hello, everyone. We have Ben Lee Wolk, the group from Caltech. Hello, everyone there. We have Irfan Sadeki Azer from Indiana University. Thanks for joining. Hug Bennett from Northwestern. Hello, guys. Hi, Hug. And we have Leo. I'm not sure where you're from, but welcome anyway. We have Muhammad Jiabadi from UC Berkeley in the group. Hello, everyone. And not sure where you're from either, but hello, Muhammad. And finally, we have Shenggen Wang from University of Michigan, not far from Chris Peikert. Okay, so hello, everyone again. So today's talk will be given by Chris Peikert. So Chris graduated from MIT under the supervision of Silvio Micali in 2006. He was at SRI International for some time, then moved to Georgia Tech for 6 years, and now he is at University of Michigan. Chris is expert in lattice-based cryptography. Today he'll also be telling us about something related to that. Among other awards, he won 2 Best Paper awards, and also more recently the Test of Time award for one of his works on making lattice-based cryptography more efficient. So without further ado, let me start the talk. Hello, Chris. You can go ahead.
All right, thank you. Thanks, Aded, for the introduction, and to the TCS Plus organizers for inviting me. And thanks everybody for coming virtually today. Just to let you know, my camera doesn't work, so you won't be able to see me. And to make things fair, I'm also not able to see you. But if there are any questions throughout the talk, please feel free to pipe in and ask them. I'll also include a lot of breaks and ask for particular questions at various times that expect they might be coming. So this is a work called Noninteractive Zero Knowledge for NP from Learning with Errors. It's with my student, Sina Sheehan, who is graduating shortly. And if you're looking for a terrific postdoc, look no further. You should definitely hire him. So please talk to me or Sina after the talk if you're in the market for somebody great. Okay, so to begin, the topic of the talk is zero knowledge protocols, which were introduced by Goldwasser, Micali, and Rakoff in the mid-'80s. And these are protocols which allow a prover to convince a skeptical verifier that a statement X is in some language L, but while revealing nothing other than that fact that X is in L. And the classical example of a zero knowledge protocol is the one for graph isomorphism. So here we have 2 graphs, G0 and G1, and the prover knows that G0 and G1 are isomorphic via some witness pi that is an isomorphism between the 2 graphs. So the prover wants to convince the verifier that the graphs are isomorphic, but only that fact. So the way this protocol works is quite simple and very elegant. First, the prover chooses a random permutation of graph G0, let's say arbitrarily, and calls that graph H. So randomly permutes G0 to get H and sends H along to the verifier. The verifier then challenges the prover via a bit, a randomly chosen bit B from 0 or 1. And this bit can be interpreted as asking the prover or challenging the prover to show that the graph H is isomorphic to G sub B. Naturally, the prover can oblige and can answer this question. If B is 0, then the prover merely hands over the permutation row that it used to permute from G0 to H. If the bit is 1, then the prover composes row with the permutation pi that connects G0 to G1 and sends over the appropriate permutation to the verifier. And the verifier can then check that indeed the original random graph H is equal to the permuted graph G sub B. So this protocol has three main properties. The first is completeness. Naturally, if the two graphs are isomorphic and the prover has an isomorphism between them, then you can complete all the instructions and convince the verifier. Secondly, it's sound in the following sense. If the graphs are not isomorphic, if G0 is not isomorphic to G1, then a cheating prover P star is able to convince the verifier only with probability at most 1/2. And this is because once the prover, the cheating prover P star sends over some graph H in the first message, it's basically locked down. It's basically, it can only answer one of the two possible commitments because H can be isomorphic to at most one of G0 or G1. And so with probability 1/2, the verifier challenges the prover on the graph GB that it is not isomorphic to H, and the prover cannot complete the third message. Naturally, the soundness error can be reduced exponentially simply by running this protocol in parallel, let's say M many times. So that is, the prover simply sends a bunch of random permutations of G0 in the first round. The verifier sends back M uniformly random and independent bits, and then the prover replies with the appropriate permutations, and the verifier checks each of these permutations in parallel. Finally, the protocol has this nice property of zero knowledge, which is that intuitively the verifier learns nothing more than a random permutation of G sub B with H. So it just learns a random permutation of a graph of its choice, well, either G0 or G1. Formally, we say that the zero knowledge property holds because one can simulate the at least the honest verifier's view of the protocol whenever the two graphs really are isomorphic. So the verifier is convinced that the graphs are isomorphic due to soundness, but it does learn nothing more than that fact, because everything it sees, it could have simulated itself in the simulation. So zero knowledge is great for these ad hoc problems like graph isomorphism, but what we would really like is to be able to prove any provable statement. That is, we'd like zero knowledge for all NP languages. And in fact, in 1986, Goldreich, Macaulay, and Vigderson showed that assuming one-way functions exist, then every NP language does have a zero knowledge proof. And this was extended in 2006 by Nguyen, Ong, and Vadan to zero knowledge arguments that are statistically zero knowledge. So this is a fundamental result with many applications. It basically allows you to prove that you're behaving honestly in any kind of scenario. That is an identification scenario, that you're not impersonating somebody else. It's used widely in multi-party computation to prove that that entities are behaving according to the designed protocol and not maliciously departing from the protocol they're supposed to be running. So very important theorem overall with a ton of applications. In order to get this result, it's sufficient to give a zero knowledge protocol for a single NP complete language, because then by NP completeness, we can reduce any NP language to that NP complete language and then run the protocol for that NP complete language. In particular, Feiga, Lapido, and Shamir in 1990 gave a very elegant protocol for a Hamiltonian cycle problem, which will be of interest to us today. So the way this one works is that we have some graph G, and the prover also has a cycle C in the graph and would like to prove to the verifier that such a cycle exists without revealing anything more than that fact. So the way this works is similar to the previous protocol. First, the prover chooses a random permutation of the graph G, that should be G, not G0, and calls that H. And then what it does is it sends a commitment to the graph H in the form of commitments to the adjacency matrix. So what the prover does is looks at the adjacency matrix of H and then commits to each of those bits individually. We call those C sub ij. and also commits to the permutation row that connects G to H. So this commitment is an object that we can build from one-way functions. And essentially what it does is it hides the contents of the commitment from the verifier, but it also binds the prover in that once the prover sends over a commitment, that commitment can later be opened to only one possible value. So no matter what the prover sends over in this first message, these commitments can be opened in only one way each. So after the prover sends over these commitments, the verifier then, as in the previous protocol, just chooses a random bit B. And the interpretation of this bit is a little bit different from before. If the bit is 0, then the prover simply opens all the commitments to the edges Hij, the indicator variables, that is, of the edges, and the permutation row. And the verifier simply checks that indeed H is the permuted graph G under this permutation row. However, if the bit is 1, the prover does something different. In this case, it simply opens the commitments to all the edges Hij, which are in the permuted cycle. So row of C is now a cycle inside of H, and the prover simply opens all those edges or decommits rather to all those edges, and the verifier checks that those commitments, that these decommitments are correct, and that they do indeed form a cycle inside of the graph H. So all the other edges of the graph are left unrevealed, but the verifier knows that there is a cycle inside this graph H. So the reason why this cut and choose protocol works for soundness, for example, is that if there's no cycle inside of G, then the prover is kind of stuck. It can either commit to something which is not isomorphic to G, in which case the verifier would catch it cheating with bit B equals 0. Or if the prover does commit to something that's isomorphic to G, the verifier will catch it in the case that B equals 1. The prover will not be able to open legitimate edges in the graph that are forming a cycle. So that is, in order to answer both possible challenges, the prover must actually commit to a graph that has a cycle and that is isomorphic to G. The zero knowledge property is also intuitively easy to see. The verifier either sees just a random permutation of G, which it can generate itself, or it sees a random cycle inside of some committed graph where it doesn't see any of the other edges in the graph. Okay, so this is a good time for any questions about this, because the protocol will show up a bit later. Okay, great. So zero knowledge is great, but interaction that's required for these protocols is not always possible in many scenarios. And so Blum, Feldman, Macaulay, and Blum, DeSantis, Macaulay, and Persiano in the late 80s considered a model called non-interactive zero knowledge. So they asked the question, what if the prover simply just sends a message to the verifier, a proof pi to the verifier, and then the verifier either accepts it or rejects it? Could we potentially make these proofs also zero knowledge while still be non-interactive? And the answer is unfortunately not. In this plain model that we've shown, the only statements you can prove, or the only languages that have NIZK proofs are those in BPP. So just the trivially decidable languages by the verifier itself. However, if we change the model slightly to introduce some kind of setup, then things become more interesting. So what they envision in these works is that there is some kind of common string, either a common random string that's known to both the prover and verifier. And you can think of this random string as maybe being some background radiation coming from the universe that we measure, or it's the lottery numbers for the past year or something like that. So some source of trusted randomness. Or in a stronger model, one could consider a reference string, which is set up by some trusted party. It may have a non-uniform distribution, but it's set up by some trusted party who then goes away and is not involved in the protocol. So in either of these models, one of these two models, it was shown that indeed we can give NIZK proofs for any NP language under various cryptographic assumptions. These include things like quadratic residuosity or trapdoor permutations. Groth-Ostrovsky Sahai in 2006 used pairing-friendly groups, hard problems with bilinear pairings. And then more recently, Sahai and Waters used a very powerful object called indistinguishability obfuscation to give NIZK proofs for all NP languages. And there are many applications for this. Anytime you would like to have zero knowledge, you'd like to prove proper behavior or that things have been done correctly in a non-interactive way, you might be able to use non-interactive zero knowledge. And so the applications include digital signatures, encryption that's secure under chosen ciphertext attack. Cryptocurrencies are using such proofs very heavily as well, and many other applications to this object. However, it's unfortunately been open, going back at least to 2007 or so, whether these NIZK proofs for NP could be constructed under an assumption that is post-quantum or secure against quantum attacks. And a primary foundation for those would be using lattices or the learning with errors problem of Oded from 2005. There were many failed attempts in the past 12 or so years to solve this problem. I know because at least a dozen of them were mine. And then there were many bits of partial progress over the years as well, but it remained a very frustrating situation that we could not construct this very basic object from lattices when we can do all kinds of other amazing things using lattices like fully homomorphic encryption and lots of other astounding cryptographic objects. So this problem has been open at least for 10 or 12 years. And in fact, I think in 2015, a $100 bounty was put on it by Vinod Vaikunthanathan, and we have come to collect. So our main theorem, following some recent progress on this question, is that indeed there are NIZK proofs for all of NP, assuming that the plain LWE problem is hard. And that assumption is supported by the conjecture that lattice problems are hard in the worst case. So in particular, this is the first NIZK construction for NP that's based on a worst case complexity assumption. Are there any questions at this point? Great, okay, we will soldier on. So our construction follows what's known as the Fiat-Shamir heuristic, and this goes back also to the mid-'80s when zero knowledge was very new. So Fiat and Shamir proposed a way to remove interaction from public coin protocols. Public coin meaning that the verifier just chooses random bits as its challenge to the prover, much like in the past, in the two example protocols we've seen. And the idea for removing this interaction is simply to use some kind of hash function. So if on the left we have some protocol, interactive protocol that is, with this structure that the prover speaks some message alpha, and then the verifier just sends a random challenge beta, which is just a random bit string, m bit string, and then the prover answers with message gamma, we can convert this using the Fiat-Shamir heuristic into a different proof system, where in the common string, we have the description of some hash function h, and then the prover simply sends a single message to the verifier by preparing its first message alpha as usual, and then letting beta equal the hash of that message alpha. So it doesn't have to receive beta from the verifier, it simply hashes alpha and acts as if the resulting beta is the verifier's challenge. And then finally, it completes the proof with the message gamma as before. So in this way, the proof system can be made completely non-interactive. And the question is, what properties does it have or does it retain? And it's pretty easy to see that completeness, that is, the prover can convince the verifier when the statement is true. That's retained. That's trivial to see. Moreover, zero knowledge for honest verifiers is also easy to preserve in this situation. In order to prove zero knowledge, basically one would simulate the alpha, beta, gamma messages as in the interactive protocol. And then the simulator would basically program the hash function in the common string to make alpha hash to the value beta that was chosen originally. And it's very easy to design hash functions that allow you to program them at one point like this. Basically, some kind of one universal hash function does the job there. So the completeness and zero knowledge properties are really trivial to retain here, and we won't really speak of them any further in the talk. The key question in this Fiat-Shamir methodology is really soundness. And the question of soundness is, after we make this transformation, are there messages alpha and gamma with beta equaling the hash of alpha that would end up fooling the verifier in the non-interactive transformed protocol? And a related question is not only do such alpha and gamma exist, but could a cheating prover actually find such values given the hash function? And this is basically the question of proof versus argument. If we would like an actual proof, we would want to say that there do not exist any alpha such that beta lets the prover fool the verifier. Or we could ask a different question, which is maybe it's intractable for the prover, a cheating prover, to find such values, alpha and gamma, that would fool the verifier. Okay, so any questions about the Fiat-Shamir methodology so far?
What prevents the prover from just trying a few values of alpha until you get one that works, assuming beta is only 1 bit?
Right, so beta if beta is 1 bit, then that indeed does work. Just try a bunch of values of alpha, and you can try values of alpha for which you know how to answer one of the 2 possible challenges beta. And so you could just keep trying them until you find one that hashes to the bit that you know how to handle, and that would violate soundness. In this case, notice that we're considering a challenge beta which is m bits long. So we imagine m being very large, and so the soundness of this protocol on the left, we would want to have very small soundness error, something like 1/2 to the m. And in that case, it's less obvious how a prover could try a bunch of alphas until it gets a suitable beta, because the beta is coming from a large space of size 2 to the m. Okay. Any other questions about this? Great. Okay. So again, the key challenge for Fiat-Shamir is to retain soundness. And a number of works over the past couple of years have made quite a bit of progress on this question. In particular, there are works by Kalai, Rothblum, and Rothblum, Canetti, Chen, Raisin and Rothblum, Holmgren and Lombardi, and most recently, Canetti, Chen, Holmgren, Lombardi, Rothblum, and Wicks. And I will give myself a prize for remembering all the authors here. So the setting is the Fiat-Shamir methodology is depicted here in the picture. And what these works show in a nutshell is that in many cases, for many kinds of protocols, what suffices is to use a so-called collision intractable hash family H. A collision intractable means the following thing. If we choose a hash function H at random from the family, then it is either either intractable or impossible to find an initial message alpha, such that alpha and its hash together are in some relation of interest. And the relation of interest here is the set of all alpha comma beta pairs for which there exists a third message gamma that will fool the verifier. So if we put things in this language, and it's really not changing anything, this is just kind of introducing new syntax or a new concept. What this is saying is that given a random hash function from the family, we want it to be hard to find an alpha whose corresponding beta has a gamma that would fool V. So that's the task at hand. And from now on, we can really ignore gamma from now on. The interest really is only on these alpha beta pairs and whether we can find an alpha that hashes to an appropriate beta that would fool verifier. So the theorem, one of the main theorems, which uses an idea from Holmgren-Lombardi and then is proved formally in Canetti et al. They show that there is a NIZK proof system for any NP language, assuming that one has a collision intractable hash family for all bounded circuits. So what they're asking for here is a collision intractable family for a whole class of relations. And these relations have the form where the first component, alpha, is arbitrary, and the second component is just some fixed function C of alpha. And the C is some circuit, concretely, of some bounded size S. Right? So what we have here is a particular class of relations where the witness for each value of alpha, there's a unique witness, or at most one witness, which is computable by a circuit of bounded size. So they show that if you can build such a hash family, then you get a NIZK proof for all of NP. It's instructive to see the main proof idea behind this theorem because it's really quite lovely. So what they do is they consider the Hamiltonian cycle protocol repeated in parallel m times. So from before, but repeated in parallel. And notice that each potential prover's first message alpha, for each such message, there is at most one bad challenge beta that would allow V to be fooled. So there's really only one unfortunate choice of beta that will allow a prover to fool the verifier in this Hamiltonian cycle protocol. And the reason why is, remember that let's consider just a single repetition of this protocol. In the first message, the prover commits to a graph, and that graph is supposed to be a permutation of G. It's supposed to be H, which is a random permutation of G. At that point, the prover, in the case of soundness, G does not have a cycle. And so the prover has to decide, am I going to commit to a graph that is isomorphic to G, or am I going to commit to a graph that has a cycle? It can only do one of the two things. And so there's basically one bad choice of beta and potentially one good choice of beta that allows it to cheat. When we repeat this m times, for each slot has the same dilemma presents itself to the prover. And so no matter what the prover sends in the first message, all these commitments to m different graphs, there's one choice for each slot that it knows how to answer. And so overall, there's one bad challenge beta that would allow the prover to fool V. Moreover, this bad beta is actually efficiently computable by using what's known as a trapdoor for the commitment. So there's if one uses an appropriate kind of commitment scheme, there exists a trapdoor which allows one to open up those commitments and actually look inside of them. And from that, one can determine, is the commitment to a graph that has a cycle or doesn't have a cycle. And remember also, the commitment includes the permutation row that's supposed to link H and G. So with this in mind, the overall statement, again, is that if we can build a collision intractable hash family for these circuits, which compute these efficient circuits or bounded circuits, which compute the bad challenge beta given the initial message alpha, then the Fiat-Shamir methodology is sound when applied to this Hamiltonian cycle protocol. Okay, so there's quite a bit there, but I'll take a pause for any questions.
One question. So you don't care about the hardness of finding gamma, right?
That's correct, right. It's not relevant here. All that matters is, can you find alpha?
I see. So are you talking now about the hard case or the impossible case? Is it computational or not?
It could be either way, and I don't want to commit one way or the other. The collision intractable family could make it hard to find such alpha, or it could make it impossible to find such alpha. Either way works. It will give you either a proof or an argument.
So for it to be impossible, all you have to make sure is that the hash of alpha is not equal to C of alpha?
That's correct. For no for no values of alpha, is that the case?
And the difficulty is that the hash doesn't know the trapdoor, right?
That's correct. The hash doesn't know the trapdoor. Moreover, the hash family doesn't actually know which C we're interested in advance. So the statement here requires a hash family which is intractable for a whole class of relations, R sub C. So that's what makes this somewhat non-trivial. If it were just a single circuit C, then one could just define the hash function to compute C of alpha and then take the complement or something like that. And then it's trivially collision intractable. But here we need it to be intractable for a whole family of these circuits. Okay. Any other questions about this? All right, it's not too essential that you understand the proof. This is just the 3-line version of it. But what is important is that we are now aiming to get a collision intractable hash family for bounded circuits. So the prior works that I mentioned here were also interested in obtaining collision intractable hash families. And the CCRR work constructs such hash families for all sparse relations. Although they rely on rather exotic assumptions in doing so, like optimal hardness. Holmgren and Lombardi showed a similar result, collision intractability for all sparse relations from a strong form of code obfuscation and other assumptions. And then the most recent Canetti et al. Work showed a collision intractable hash family for all bounded circuits, which is exactly what we want, but it makes the assumption that circularly secure fully homomorphic encryption exists. So this is a form of fully homomorphic encryption where it is additionally secure to give out an encryption of the secret key. This is what circularly secure refers to. So such an assumption is not all that uncommon. In fact, circularly secure FHE is the only way we know how to obtain full unbounded fully homomorphic encryption. And yet, while this seems tantalizingly close to LWE, we don't know how to get circularly secure FHE from standard LWE or from worst case lattice problems. So nevertheless, this looks very close to what we would hope for. And our main construction finally closes this gap. We've managed to give a collision intractable hash family for all bounded circuits using just the plain LWE assumption, no circular security needed. And in fact, the assumption that we need is only for small approximation factors. If you know what that means, that's fine. If you don't, that's okay too. So similarly to the Canetti et al. Work, our construction actually can be instantiated in 2 modes or 2 forms of intractability, going back to Ed's question. So the first form is computational intractability, which says that given a random function from the family, it's simply hard to find, or it's infeasible to find an alpha such that h of alpha equals c of alpha. And if we use that mode and plug it into the Canetti et al. Theorem, then we get statistically zero knowledge, but computationally sound arguments. So what this says is that a verifier learns nothing other than the truth of the statement, even if the verifier is computationally unbounded. So it's an information theoretic security against the verifier. But the soundness of the proof system holds only against efficient cheating provers, i.e. this is an argument. And this works in the uniformly random string model, which is the model that one would prefer. It's easy to implement. The second intractability mode is the statistical one, which basically says that if you have a particular circuit in mind and you choose, you can choose a hash function from a family that is computationally indistinguishable from the actual one. And with that, such an alpha does not exist at all with high probability. So there do not exist, for an H chosen from in this way, there simply does not exist any alpha such that H of alpha equals C of alpha. And if we use this mode of the hash family, then the properties of the NIZK are flipped around. The NIZK has computational zero knowledge against feasible cheating verifiers, verifiers using polynomial computation to try to learn something from the proof. But the proof itself is statistically sound. That is, proofs for false statements simply do not exist. And this holds in the stronger common reference string model.
So this is weaker, right? I mean,
I'm sorry?
Stronger in this case means it's a weaker result, right?
Yes, it's a stronger model. It requires some kind of setup from a trusted party to choose this reference string. That's right. And these, I should reemphasize that these two modes and these two options for how the NIZK, the properties that it has, can also be obtained from the Canetti et al. Paper, but under this circular secure FHE assumption. Okay, so any questions about the main construction so far? All right.
So maybe one thing, Chris, I'm not sure how much it matters, but in the second one, the statistical one, it's a bit strange. It depends on the circuit that you wouldn't even know because you don't know the trapdoor.
Right. So in fact, yeah, that's a good question. You in fact do know the trapdoor. So yeah, this is a little bit sensitive, but the setup of the reference string can be done in a way where the circuit C that you want is actually known to the person setting it up. So the person doing the setup knows the trapdoor and therefore knows the particular circuit C that it wants to be intractable for. If that makes sense.
So I see, but both have to know H, right?
Both have to know H, that's correct.
Okay. Okay, thanks.
So the overview, there's kind of two parts to the construction. The first is to give a correlation intractable hash family for NC1 or log depth circuits from LWE, or even from what's known as the short integer solution problem. And then the second part is what we call a bootstrapping theorem. And this gets you from correlation intractability for the decryption circuit of an FHE scheme, a leveled FHE scheme that is, which does lie in NC1, to arbitrary bounded circuits. And this bootstrapping works very much similarly to Gentry's initial bootstrapping technique from his breakthrough FHE work. And such fully homomorphic encryption can also be based on LWE. I'll note that for the NIZK application, we actually don't need this bootstrapping part because the bad challenge functions that we are wanting to be correlation intractable against can be implemented in NC1 using a trick that was sort of buried in these earlier papers. It's not clear exactly where, but this was pointed out to us by Lombardi. So we just need the first component, which is correlation intractability against log depth circuits. So to do this, we're going to use the short integer solution, or SIS, and LWE problems, which were introduced by Aitai and Regev respectively. And I'll just briefly say what these problems are. So for these problems, we have a modulus Q, which you can think of as some moderately large polynomial in N, and then some dimension N and another dimension M, which you can think of as about order n log q. The dimension m is basically the bit size of n numbers mod q. So the SAS problem is simple. We're given a uniformly random matrix A, which is n by m with entries modulo q. So it's this kind of wide rectangular matrix A. And the goal is to find some short vector z such that A times z equals 0. And by short, we mean the Euclidean norm of this z should be quite small. You can think of it as z should be 0, 1 vector, or a vector whose entries are much smaller than q. So this is just a linear system, but with the additional constraint that the solution has to be small in Euclidean norm. The LWE problem is somewhat similar. It's a distinguishing problem. So the problem is to distinguish a uniformly random matrix A having these dimensions from one where having the same dimensions, where the top of the matrix, all the top rows are uniformly random, but the bottom row is a combination of the top rows plus a little bit of noise. So this plus a little bit of error here. So again, we have a uniform n-1 top rows, and then the final row is just some combination of the top rows plus a short error e. And the goal is to distinguish one case from the other. That is, I give you a matrix and which has either this form, it's totally random, or it has the structure to it, and you need to distinguish between the two possibilities with some noticeable advantage. We know quite a bit about these problems, but the bottom line in one line is that worst case lattice problems reduce to solving these problems, SAS and LWE, on the average. So we have these famous worst case to average case reductions, which show that solving these problems on the average is at least as hard as approximating certain lattice problems in the worst case. We need one more tool for our construction, which is the following. There's a linear function, which I'll call G, which maps binary vectors of dimension m into n-dimensional vectors over ZQ. And you can think of this as just taking, so m is roughly 2n log q. So you can think of this function as taking each chunk of 2 log q bits and treating it as an integer and reducing mod q. So in the end, you get a vector of n numbers mod q. And in a sense, this operation can be reversed in a nonlinear fashion, but we can go backwards. That is, we can take each of the numbers mod q, and we can write their binary representation using 2 log q bits, and then form a vector, a binary vector of dimension m of the results. And the property that we need is that these are in some sense inverses, at least in one direction. So if you take G inverse of U and then you apply G to that, you get back the original U. This basically says if you take the mod Q numbers, write them in binary, and then convert them back and reduce mod Q, you get back the original vector U. Nothing terribly interesting there, although what's important is this function G is linear.
You mean by linear? There's no defined field here. I'm not sure what it means.
So if you sum 2 inputs over the integers, let's say, then the outputs will also be summed.
Over the, not modulo 2, over the integers.
Not modulo 2, right, over the integers. Yeah. So sum these up over the integers, and the results will be added mod q in the range. So
okay, so it's not really defined over 0, 1, 2, but if it were.
Yeah, that's right. Yeah. So yeah. Although we'll only use it over 0, 1 values.
Okay.
Okay, so now we can talk about our correlation intractable construction. So again, the goal here is to be correlation intractable for a size S circuit that maps some arbitrary L input bit to M output bit, and this N is the same M as in the SAS and LWE problem. And what we're going to use here is the fully homomorphic encryption, or rather commitment scheme, that is in Gentry Sahai Waters and was treated as a commitment scheme by Gorbunov, Vaikuntanath, and Wicks. So the key to our hash function will simply be a commitment, fully homomorphic commitment, which I'll denote d hat, to some dummy circuit. This can be any circuit whatsoever of size S, having the appropriate domain and range. The way that we evaluate the hash function is as follows. So we're given an input alpha, which is from the domain, so it's a length L-bit string. The first thing we do is we use this commitment d hat to homomorphically compute a commitment to d alpha. So this hat denotes, still it's a homomorphic commitment, but now it's to d alpha. So we evaluate the committed circuit here on the input alpha to get a commitment to d alpha. Then we do something a little bit different. We do another homomorphic evaluation, but it's of the certain linear function g from the previous slide. So we apply this, evaluate rather, this linear function g homomorphically, but we do it in a special way to flatten it out into what we call an inert commitment. We call it an inert commitment because it doesn't seem to allow any further homomorphic operation. So I denote it by this flat line over the top instead. We have the commitment C alpha, which is now an inert commitment to G of D alpha. And the important thing is that this inert commitment is a commitment to a value in ZQ to the n, but the commitment itself is also in ZQ to the n. Finally, what we'll do is just output this G minus of the inert commitment. So that's essentially the binary representation of C alpha here. So the two steps, again, are homomorphically evaluate this dummy circuit on the input alpha, and then flatten it all out while also applying this linear function to the underlying committed value here. It's interesting, I think, I'll just mention briefly how this differs. There are some similarities and also differences to the Kennedy et al. Construction. Kennedy et al. Use, instead of commitments, they use fully homomorphic encryption. So they use a ciphertext. And here they do encrypt a dummy circuit, but they also need to include a encryption of the secret key, of the FHE secret key. And this is where the circular security is required. Their step one is the same. They do this fully homomorphic evaluation of the dummy circuit on the input alpha. In the second stage, it's quite different. They apply this secret function, which is the decryption function using the secret key to this, and they don't flatten anything out. They get an ordinary FHE ciphertext at the end, which is not inert. It's still computable. You can still do homomorphic operations on it. But for our purposes, it's really important to get this inert commitment here at the end. And the key point is that the inert commitment C alpha here, the commitment itself lives in a ZQ to the n, the vector of n integers mod q, but it also hides a value in ZQ to the n. And what this will do, it will allow us to compare these two things directly to each other. We're going to compare the commitment itself to the hidden value inside of it. And we're not just going to reason about the hidden value inside of it as Kennedy et al. Do. And this is really the key thing that's going to let us avoid the circular security assumption. So I'll take any question about how the hash function actually works before we sketch out the proof.
One question, Chris, is you're mentioning here both LWE and SAS, but I'm not sure why do you need both. It would be enough to do it based on SAS, right?
Right. So this construction, as I mentioned before, or should have mentioned before, we can prove it under SIS to have computational intractability. We can also prove it under LWE to have statistical intractability. So we get different properties based on which assumption that we use.
And are we supposed to understand what you mean by this overline for the inert, or is this something we're going to look later?
I'll talk about it on the next slide.
Okay.
the main point is it's a different kind of commitment. The flat line indicates that it's inert, and that means you can't do any further homomorphic operations on it, but we don't need to. So the real key here again is to kind of flatten out these fully homomorphic commitments down to an inert one in the step 2 here. And we'll see in a little more detail now why that matters.
One last thing.
Yeah, go ahead.
What is exactly the dummy circuit?
Oh, the dummy circuit, it's just any circuit mapping L bits to M bits. It can be some canonical circuit. Can always output 0.
So it's just a circuit always output M-bit 0 string.
Right.
Okay.
We will use something more useful in the security proof.
Okay.
So let's talk about the security proof here. So we want to prove security from the SIS problem. And just to recall, the hash key is a commitment to this dummy circuit, a fully homomorphic commitment. And when we're evaluating the hash function, we compute D homomorphically on alpha, and then we flatten it down to this inert commitment, and we output the binary representation of that. So we want to show that this function is correlation intractable against any circuit C of size S. So pick some circuit of interest. And now suppose that we have an adversary that when we give it the hash key, the hat, is able to find an alpha such that H of alpha equals C of alpha. So we're proving the computational intractability here. There's some adversary who's capable of doing this, then we're going to exhibit a reduction that solves SIS. So the first step of this reduction is to notice that by the security of the commitment scheme, the adversary will still work if we give it a kind of fake hash key. If we give it a hash key which is a commitment to the circuit C instead of the dummy circuit. Okay, so what we're doing is we will instead feed the adversary a commitment to the circuit C of interest. And now the evaluation, what the evaluation is computing is now different. It's now an inert commitment of G of C of alpha up here. So let's notice what happens. If we apply G, this linear function G to both sides, then what we have is that this outer G inverse is canceled. And so this inert commitment C alpha is just a flat line of G of C alpha, this inert commitment to G of C alpha. And that's applying G to this left-hand side here. Oops, sorry. That's applying G to H, but also applying G to this right-hand side of C of alpha gives us this right-hand side here. So in other words, the inert commitment that the hash function computes, this C alpha inert commitment is itself equal to its contents, which are G of C alpha. So the commitment is both a commitment to G of C alpha and itself equals G of C alpha. And the technical theorem that we show here is that using the commitment coins for the original commitment to the circuit C, we can then derive commitment coins R alpha for C alpha, and this will solve the SIS problem. Okay, so our goal at this point is to show that essentially if you're able to come up with such a inert commitment that equals its own content, and you know the coins for that commitment, you've actually solved SIS. So that's what we'll show here. So again, we have the hash key is this commitment now to the circuit C, and it's a commitment to C under coins R sub C. And then the evaluation is computing an inert commitment, which itself is equal to G of C alpha. And this is a theorem we want to show. So in order to show this theorem, we need to use a little bit of knowledge about how these commitments work. The first thing is that the initial commitment C hat is well, all the commitments really are with respect to an SIS matrix A. So there's a uniformly random matrix A, and the coins themselves represent some kind of short vector. So concretely, the C hat commitment equals A times the coins plus some encoding of the circuit C, and it's not too important how that works. But it has this kind of structure. In step one, when we homomorphically evaluate C on alpha, what was shown by the Gorbunov et al. Paper is that from the coins of the original commitment, we can efficiently compute the coins of the C alpha commitment. So the homomorphic evaluation gives us a way of also evaluating the corresponding coins for the derived commitment here on the left. So now what we have is the commitment to C alpha is A times some known coins R plus an encoding of C alpha. That again doesn't matter. What we show in this work is that from those coins R, we can compute the desired coins that we want, the coins R alpha for the inert commitment C alpha. That is, the inert commitment on the left here, so the line over G of C of alpha, will have the form A times coins R alpha that we know, plus the actual committed value here without any special encoding. So this is the actual committed value G of C of alpha. So the inert commitment has this form for coins R that we know, but now observe that in fact, the commitment itself by assumption equals the committed value G of C alpha. So this is the equation that we have. And now basically we're home free. What we notice is that we can just remove the G of C alpha from both sides, and we're left with A times R equals 0. And this is the desired solution to SIS that we wanted. So to recap here, we have an SIS matrix A. We provide the commitment C hat to the adversary using coins that we know. The adversary tells us an appropriate alpha that makes the hash of alpha equal C alpha. And then we go through this process, we, the reduction, go through this process to compute the coins R alpha for the inert commitment. And by the properties of the inert commitment, these coins R alpha are actually a solution to SIS. And that's it. Any question about this? It's a little bit quick, but that's the overview of it.
You probably need to argue somewhere that R alpha is not 0.
Oh, that R alpha is not 0. Actually, that didn't occur to me. I'm just kidding, it occurred to me. We also have to make sure that R alpha is not 0. And this is an easy tweak. So you just make the calculation inhomogeneous, and it's a simple thing to do.
I know you well enough. It didn't work.
Didn't fool anybody. Okay, well, I tried. Right. So indeed, we do need to make sure that the solution is non-trivial, and that's an easy thing to do. Okay. So in the interest of time, I think I'll refer you to the slides for how this computation of the inert commitment works, because it's the kind of the new technical part. This inert commitment property is what allows the whole proof to go through. But I won't go over that in detail. But it's not very difficult, especially if you know something about the literature. Okay. Also, in the interest of time, I'll just briefly mention the LWE-based construction. So this SIS-based construction that we just showed has the property of computational correlation intractability, and it has a uniform key. So that is, given a uniform key, the attacker, it's infeasible to find an input that hashes to C of alpha. And that translates to a computationally sound protocol with statistical zero knowledge. So that's actually a good combination. It's a nice combination of properties to have. But in some cases, you might want a statistically sound zero knowledge protocol, and we can obtain that using LWE instead of SIS. In order to do this, we need to change the key from being uniform to non-uniform. So the way this works now is that the hash key will now be a commitment C hat, but it will be with respect to an LWE matrix A. So not a uniformly random matrix A, but one which is random on top and kind of LWE in the last row here. The evaluation works in essentially the same way as before, except that when we compute this inert commitment, we subtract Q over 2 from the final coordinate. And the reason why is shown here. So if the attacker, or really if an alpha exists, such that H of alpha equals C of alpha, then going through a similar process as before, we have that A times R alpha is not 0 anymore, but it's actually equal to this vector with Q over 2 in the last coordinate. Okay, just because of how we set up the inert commitment, how we change things. So what this tells us is that the top rows, that is A prime times R alpha, is 0 from this top part of the equation. And moreover, the bottom row, if we look just at the bottom row, that tells us Q over 2 is the bottom row times R alpha, or the inner product of the bottom row times R alpha. Now we know that A prime times R alpha is 0, so this first part here cancels out, and we're left with just the error vector from the LW matrix times R alpha. But it turns out this is a contradiction. You can't have this if you set up the parameters correctly. And the reason why is that this error vector is short by construction. This vector R alpha is also short by construction. And so by Cauchy-Schwarz, if you take the inner product of two short vectors, they're going to remain somewhat short. And we can set up Q to be larger than that bound. So what this shows is simply there do not exist any alphas that hash to C of alpha when we set up the hash key in this fashion. So that's how the LWE-based construction works. I'll take questions about it offline if there are any, because I just wanted to finish up with open problems. So one nice open problem, a little bit of a technical problem, is to go beyond log depth circuits while still assuming SIS. Currently, to get beyond log depth, we need to use bootstrapping or assume stronger than polynomial factors in our SIS problem. So this seems like something that morally should be possible, but we don't know how to do it. Another great question is to go for a relaxed object called non-interactive witness indistinguishable proofs. These are proofs in the plain model, so there's no common string, but they're not zero knowledge, but they hide which witness the prover used to produce the proof. And interestingly, Groth, Ostrovsky, Sahai get this object sort of for free or very easily from their NIZK proofs because they have statistical soundness in the random string model. But we only have computational soundness in that model, and so their trick just doesn't work in our setting. So the question is there something else that one can do? But these NIWI proofs have a number of nice applications, and it would be nice to have this object. A couple of other questions. One is compactness. So our hash key grows as dependent on the size of the circuit that we want to be intractable against. That's not the case with constructions that are based on exotic assumptions like code obfuscation. So those constructions have a hash key that doesn't grow with the size of the circuit. And it would be nice to get that without such strong assumptions. And finally, a really interesting but probably very hard problem is to get succinct zero knowledge arguments from LWE, ideally in the non-interactive setting, maybe via Fiat-Shamir or something like that. Succinct meaning that the size of the proof is only growing, is not growing with the size of the witness, for example. But I'm sorry. But let me leave it not totally formally define what succinct here means, but basically stress that we want much shorter proofs than what this technique gives us here. And there's many other really interesting questions that come up, but I will conclude with that. Thank you.
Thank you, Chris. Questions?
Take other questions.
Yes, please. One.
I can't actually read the questions, so someone else could read them to me.
I think. Yeah. Are there any questions? People are very shy. Okay. Give a few more seconds. So can you maybe say a couple of words about the need for the inertness?
The need for what?
The inert. So you have the inert commitment.
Oh, the inert commitment. Yes. Well, it's because it works. I think just to go back to this part here. Okay, so the inert commitment is on the left here, and we know that the inert commitment hides the value G of C of alpha. So this is the equation defining an inert commitment of G of C alpha. And then what we know is that the inert commitment itself equals the value that it hides. So really the whole key here is showing that, is noticing this fact, right? If we have an inert commitment to a certain value and the commitment itself equals that value, then the only way for that to happen is if the coins satisfy A times R equals 0.
So that's the definition of an inert commitment? Is this how it's defined?
Well, the inert commitment is of the form A times coins plus a value in ZQN. And so if the commitment itself equals that hidden value, then you get this equation on the right, and it tells you that your coins are solving SIS.
So it's inert because it seems like you can no longer do any homomorphic encryption. It's not that you can prove that you cannot, but
that's right. It doesn't seem to support. It actually supports addition, homomorphic addition, but not multiplication.
But that's not saying that's not the goal. The goal is to encode somehow the SAS instance in there. Is that
right? Right. So the goal, the goal of having the goal is not to have an inert commitment. That's a means to the end. But I would say that the fully homomorphic commitments that we're working with in the earlier stages of the computation, they hide small values, like they hide a bit using a very large commitment that's much longer, much bigger in size. And so you can't compare the hidden value to the commitment itself. They're just of the wrong type. They're different sizes. And so doing such a comparison doesn't make any sense. But here in the proof, when we are able to compare them directly, then we get the desired equation that solves SIS.
Great. Any more questions? Okay, if not, thanks everyone for joining. I hope to see you again in a couple of weeks. And we'll take us offline, but everyone is welcome to stay and chat offline. So thank you,
everyone.